Hello everyone. Hope I'm audible. So we will just wait for 2 or 3 minutes and then we will start. Hi Akshay, I think we shall start now.
Sure. Hi, Vritam. Hello, everyone. A very good evening to you all.
Good evening, Akshay.
Hello, hi Akshay. Good evening.
What's your take?
This uh, can that is the default option in this.
In Microsoft Teams, there is an option. I don't know about this. I don't see an option. So, maybe like you can guide us. Or this is all we have for now. Like we'll try to type it in, I don't know, a month's duration of time or so. But anyway, so what are the first? So before going into details of what exactly quantum encodings are, this is a Hadamard gate. So a Hadamard gate in a tensor product forms the basis of the QFT. And there are many other QFTs like states you can produce. So this is one of the QFT states. So hence the Hadamard gate tensor product is also known as QFT first block. And this block is only used for one kind of encoding here, unitary encoding. Otherwise, we are not used Hadamard tensor protected gates here anywhere. So for other 5 types encoding, this encoding. The second is our quantum encodings, as in encoding the classical data what we have in quantum encoding format. The third is feature extraction, as in after quantum encoding the classical data, we'll walk you through on a output. What this happens is this unitary is nothing but a matrix product operation, Kronecker product operation, matrix multiplication. Whatever happens, that all accounts for a single matrix at the end of the day. So that matrix vector multiplication classical, it's nothing but a linear regression, and that too without bias under unitary constraint. So this is all about quantum computing. So that is why what we're trying to do here is feature extraction, as in if the data set is non-linear, as in the boundary of separation between the data sets is non-linear between 2 classes, then for that we have to extract the features, as in a certain transformation has to be done on the input vectors to get the feature vectors that multiplying it with a unitary will give us our resulting output or the target states, whatever classes segregation or classes classification we want as per the number of classes. So for that, like this feature extraction task will be given to you guys. So what exactly each of this block means, we'll go through that. So so what do you guys prefer? Like I can explain why, for now theory first and then code, or we can explain simultaneously, like both theory and code simultaneously. So what do you
Yes,
prefer?
yes. I think Siddharth is raising his hand.
Yeah, please go ahead, Siddharth. Yeah, Siddharth, you have a question. If you have a question, please go ahead. Siddharth, oh, okay. Let's continue. If he has a question, he'll ask. So after feature extraction, what we are doing is applying a quantum linear regression for from our end. That is the unitary of
I had
separation.
a question. My mic wasn't working, sorry. Encoding, the final unitary we are using, it doesn't have.
Yes, because what exactly this does is nothing but u into x operation. That x is nothing but an input vector, and this is nothing but a matrix. Yes.
Shouldn't we have like another input that is just constant and use it along with the unitary to introduce non-biases rather than like just having another neuron as input to introduce biases?
Okay,
And
like yes. So like it's written further. We can have another, not a qubit, but we can adjust the input vector such that the last like whatever places or the index element is, we can put one in there. But again, the issue will be after amplitude encoding, like you have to amplitude encode or you have to encode in some quantum form. So this will be scaled. So if you're putting one there, then that will be also scaled. So it will not act as a bias in this case, if you're getting the point. Yeah. So classical data, we can do that. we can add an append and one to the list or to the vector and create, like if it is 768 or 784 kind of vector cross one, we'll get a 785 cross one, where the 785th element is nothing but a bias term. And then we can multiply, we can operate further. We can have linear regression or any kind of classification, classical, and that will act as a bias, that ending term. But here we cannot do in that sense. Like I have thought about it, but yeah, quantum encoding may again rescale the classical encoded classical data set what we have, the classical vector we have.
Oh, okay.
Okay, so fine. So quantum encodings will go into detail via the code. Feature extraction, that part you have to do, that is written in the code as well. We'll walk you through that as well. And then there is unity of separation. So what exactly is the unity of separation? So here we are following a quantum inspired approach. It is not a quantum computer approach as an actual porting of this problem onto the quantum computer. It can be done, but we are not there. Hence the last. So what we are doing is directly using a PyTorch library, directly like taking the classical data set, directly encoding it without applying any unitary here. So an actual computer, if you want to quantum computer, if you want to port this problem, you have to encode each and every button, but you have to again find that unitary. So what unitary will be required to take that qubits from the ground level or the initial state of vector to this in will again be a hybrid kind of approach in that as well. But we are not porting. But depends on you. You can do the major approach in classical computer itself, or you can ignore this block. So what exactly is unitary of separation? We'll go into details of. So there are like 5-6 methods of separation. So after feature extraction or before feature extraction as well. So whatever vectors you're getting here, so that can be taken as a input vectors. If you look into, so what exactly a unitary? So this equation vectors we're getting is equal to unit into input vectors. If you ignore this part, feature extraction, then this is the equation we'll be following, right? So if a state in Kate notation, it will be output vector, Kate of output vector, and this unitary matrix, a unitary matrix operator, and this is Kate of input vector. So just if you like uh, if it will multiply matrix, a square matrix, that will be a non-unitary matrix, and then on what you can do is perform operations. So that can be a QR decomposition, that can be a SVD decomposition to get a unitary matrix. So this SVD approach will, what you will do is like you will decompose it into A, and this A into C transpose, if you will multiply, just A into C if you will multiply, what you will get is a not matrix. So that unitary matrix, this is just SVD approach. Second approach, decomposition, QR decomposition, also you can get Q into U. So this Q is nothing but our unitary matrix. This is upper triangular matrix. So this Q also you can get from this technique. There are like other approaches. Like third is the ML method. So what exactly unitary constraints are? If the first of all the rows should be also orthonormal to each other, all the columns should be orthonormal to each other. Those are the two constraints, and these constraints, if you solve mathematically, what equation you will get is U into U dagger plus is equal to I, or U dagger into U is equal to I. Those are the two set of constraints that to implement code wise. So that code also will look into, just mathematical details we are first going through. So that is our third technique. If you'll import these constraints with the constraint that unitary into input vectors should give us the output or the target vectors, that constraint, if you impose these three constraints, set of constraints, and if you follow conventional pipeline, you can impose this like you in the Python like a coding sense. And then fourth is a unitary encoding approach. Also, if you have the like matrix, as in if you'll have a non-unitary matrix of mapping, so what you'll get from here is directly the non-unitary matrix. It can directly unitary encoded following the conventional Penelian like procedure, or this is just a mathematical procedure for encoding, block encoding a non-unitary matrix matrix. Cross you have to you'll get this scalability 2 raised to n times it will increase. As in 2 raised to, if it is 8 in previous case, or 2 raised to 9 in previous case, we get 512, it will increase to 2 raised to 10, as in 1 qubit extra it will be, and it will be computationally exhaustive. But this method can also be used, and there are other two methods. So V and Britant has a paper on this. So that also you can go into details of how to get a unitary encoding for that. And this is also a parameter. Put in a U3 gate, put in a C0 gate, construct a random like a U3 and C0 gate sequences, and you can in it. So there are again 3-4 methods of backpropagation. How exactly backpropagation works in quantum sense. So shift parameter rule is one of the methods in which like you can like just by a set of like it's in the summation of two trigonometry angle, and that's the backpropagation. So you did not do a differentiation. That different issue. But what we are as well, because is a subset of the approach. Will get by what you will get by ML method, what you will get by QR decomposition methods are the best approaches for now, because QNN is the approximation again, because you have to approximate U3, you have to approximate C0, as in you have to approximate the gate, and the result will be approximate result on this. This result what we are getting by first 3 approaches are accurate, or first 4 approaches are accurate. Fifth also is an approximation approach, so we'll not follow that here. So hope like this block is clear. If this block is clear, we'll go on to the coding thing, like what exactly we have done in code. Like so is this block clear? If you have any doubts, you can ask. Yeah. Hi. Is it too fast? Like we have a limited set of time, we have to cover many things, so that's why like the speed is fast.
It is understandable for now. Yeah.
Yeah. So hopefully this thought process reciprocates with all. So yeah, moving on, like before going into the code, so let's you have understood the unit of separation part perfectly. You have understood the like Hadamard when it is with quantum encodings, you have just understood the names. So like before going to the code details, we'll explore what exactly quantum encodings and the maths behind that is, and then we'll go into the code. So to give you a sense of what exactly we are trying to do here, we are trying to get an image classification. So application of QML algorithms for start cases classification, then we'll move on to generation problems. But start we are doing with classification, because generation also has a classification block in it, and then a discriminator block in it, as in discriminator and generator block. The discriminator itself is a classifier. So if we have a clear-cut classifier understanding here, as in perfect classifier, if we made from our QML approach, then we can move on with like a discriminator with generator, which will be a quantum analog of our classical GAN. We have tried various approaches in that as well, but that will be not a part of this. So like anyway, so moving on, if you take into this image, whatever image we are trying to observe with the help of camera, that will be a digit or analog image. What we'll see in terms of like with your naked eyes are red color, green color, and blue color when superposed. So this is the equation. If you'll give a like amplitude to your R, you can give amplitude to a G, give amplitude to a B. Sorry. So this will be a sense of converging from RGB to gray channel. So anyways, like ignore this point. If you take an image, so that image what you'll observe will be an analog image. You'll see just the pixels, you'll not see pixels as well. But if you want to convert that into digital image, what you can do is pixelify that image. As in you can take if you consider this page as the whole like image, you can take a square block in this, a square block in this, so that will be 1 pixel of image, and that pixel color will be fixed. So if you take red, green, blue, so you can reproduce any color, any whatever like color, desired color. So for converting analog, that is R green matrix, a red channel matrix, a green channel matrix. So the image you are seeing will be an analog. You cannot identify the numbers. What you can do is, like if you can identify it as a 0, if it is a black pixel, you can identify it as a 255. But computer understands the language of numbers, so hence we have to convert that digital image in the physical data set what we'll be getting, and from that will be converting into the quantum. So what exactly the first? So if we'll move on. So if it is what convention we have followed here is we haven't taken all three tensors exhaustive. What we have done for our simple converted every image MNIST data set we have taken for all cases. So that in itself is a like grayscale going to the RGB channel. But even if it is the RGB image for other closing data set as well, we can try to. So if like you want to apply, that can also be done. Yeah. So like moving on. So if you take a particular like matrix, so it has a pixel value. So the pixel value is from 0 to 245 range, and in amplitude encoding is that what you're trying to do is matrix into a vector kind of setting. So you have to flatten that matrix. So if you write a quantum state, what you can write, like if you write a quantum state, A0 plus B1 is a single qubit quantum state. Like I have a notepad for that. So let's give my writing. So like if you look into this quantum state, so this quantum state, if you look into this, you all must be aware about. Like these are nothing but A and B are nothing but the probability amplitudes, and A square and B square are nothing but their probabilities, respective probabilities of occurring 0 at the state after measurement and 1 at the state of the measurement if we measure in the Z basis state. Okay. Like I'm trying to make constant if you're applying to any a vector approach. So if you write this in bracket form, that is fine. So what you can do is you write it in vector form. If you write it in vector A into 10 plus B into 01, right? So this will be a vector approach of that, right? So A and B, so you'll get nothing but the state in vector form, A and B. So that is the end goal. So as in you can write our quantum state, whatever state you have in classical set in this format, right? In the binary basis. After that, you can write it in this form of vector format. So what you have to do is normalize that. That is nothing but on amplitude encoding. Hope this is clear. Like the first encoding is clear, right? Is it clear?
Yes.
Yeah.
Yes.
So amplitude encoding like is done, and we can like I'll go into details later on, like what exactly is written here, not required for now. Unitary encoding. So like if you take image as a terms of matrix, you can directly take the image here in terms of matrix and directly normalize that image, right? If you take there, normalize that image and put it in this block and put I is again an 15. If it is a 512 cross 512 image, then it will be a 512 cross 512 identity matrix minus a into a dagger of that, and you're taking root of that. This will be root of matrix. If it is root of matrix, you have to take SVD of the matrix and then put the root onto the eigenvalues or the like singular value matrix, and then again multiply that matrix to get the root of this matrix, and this will be a 2n cross 2n matrix. So this is nothing but the unitary encoding of that matrix. And for unitary encoding, you already know, like for getting that unitary encoding, you have to first in our QML architecture, you have to multiply that with the Hadamard gate. Why you have to multiply that with the Hadamard gate? Because like the start state, you already know it is 1000, right? So if you multiply, if you take directly that as a matrix, a unitary matrix here, and you multiply that with the input state, you'll just get the first column of that matrix. You'll remove all the features. So for getting all the features or all the like you can say elements of the matrix in superposition, you're applying a Hadamard gate here, because this state will be 1 by like number root of 2 raised to n, and that whole state vector, if you are multiplying this with the input state. Otherwise it will be just 1 0 0 0 0 0 if you're getting the one. That's why you're doing this. Okay. So unitary encoding is fine. The unitary encoding has many subtypes. Instead of just amplitude encoding, like amplitude encoding has just one type, that is fine. So unitary encoding has this 5 subtypes, as in SVD decomposition. So what you can do is take the like image, you can directly SVD decompose that. You can take the image, you can directly QR decompose that, and then just take the Q matrix or just take the U into V matrix, you'll get the unitary matrix. You can directly apply ML method, as in put the matrix under constraint such that like this not this condition, the orthonormative condition or the A into A dagger of I condition is satisfied and it is near to the like original image matrix. So that can also be done. I have not tried this method yet, but it can also be tried. And like other approaches, you can go through the paper. This is also QNN method by parameterization. So like here there is a loss of info, SPD decomposition, QR decomposition, as in if you look into the number of qubits has increased here one by one to encode the classical image matrix, but here the number of qubits haven't increased. So like there is a loss of information in terms of the singular value matrix, the S matrix here, or also there is a loss of information in terms of R matrix here. So like those loss of information accounts for the loss of accuracy. If you implement this approaches, it will like you will get the losses in accuracy in QML approaches. So, but this is like saving terms of computational power. So we are following this. So what exactly the unitary matrix is written here? Hopefully, I think all know what exactly is the unitary matrix. So this has this constant U into U dagger is equal to I, U dagger into U is equal to I, and U dagger is equal to U inverse. So this
Yes,
unitary matrix,
Sai wants to
yeah,
ask some question. So guys,
yeah, Sai, please.
if you have any questions, so please feel free to ask. Okay,
Sure.
don't.
Yeah. Okay. Actually, can you just explain that SVD plays like all the three types once again? Like, why are we losing the information?
Yeah, because this USV, this is a SVD decomposition of a matrix, given matrix, right? This U is
Hmm.
nothing but if you look into singular value decomposition. If you look into it is if it is a square matrix, then it nothing but the SVD is equal to the eigenvalue decomposition. So this will be nothing but for a square matrix, all the matrices are square. So this will nothing but be nothing but eigenvector matrices, and this V will nothing but the eigenvector matrices dagger of that,
Hmm.
and this S
Hmm.
will be nothing but eigenvalue matrix. So this diagonal elements of the eigenvalues will be written in this matrix. If you could look into, so diagonal of the eigenvalue matrix is nothing but S. And if you multiply this U and V, you'll get a unitary matrix. So losing of information will be done in terms of S. So that eigenvalue matrix will be
Okay.
lost when you're converting that into unitary.
Okay. Okay. Okay.
Yeah.
Got it.
Similarly here, R will be lost. This
Okay. We
R.
are I mean, like leaving one matrix totally. So we are losing some information.
Yeah, leaving as in perfect information from to lose how many like elements if it is a square matrix of let's say n cross n, you will be losing n like elements of information.
Huh.
As
Okay.
in when you yeah, because the n
And diagonal
eigenvalues you will be losing,
elements.
right? Yeah, yeah.
Okay. Got
So
it.
yeah,
Okay, I
um,
think I have one question. So
yeah,
not from the diagonal matrix.
yes,
Oh,
yes, yes.
so what's the point? I mean, what we're trying to do here? Are we trying to regenerate the original matrix?
No. So the point here is like whatever like matrix we want to port on an actual quantum computer, that should be
Uh-huh.
under a unitary constraint, as in all the tensor product, all the like unitary gates. Whenever you tensor product with each other on a higher qubit scale, that accounts for a single unitary matrix. So the constraints of decomposing this matrix into gates, so that unitary constraint needs to be like like imposed on the data set for it to be converted as a it to be like said as a quantum approach. If you're getting the point. So constraints as in um, because we don't have
Correct,
the set
correct.
of non as in it for porting onto quantum computers. So, yeah,
Okay, so you are telling if we ignore, we will be
yeah.
getting an approximation of the original matrix into a unitary form, right?
Yeah. The nearest unitary for non-unitary matrix, original classical data. So that yes.
Hmm.
Okay, got it, got it.
In some sense, are we losing some different components, something like that?
Like if you look into exactly this account the eigenvector matrix and what exactly is the eigenvalue matrix. If you look into those details, whenever you take a vector in just a real space, if you take just a
Hmm.
two-dimensional sector, I'll draw it and show you. This is a vector in two-dimensional real space. Now, whenever you apply an eigenvalue transformation here, as in if you multiply this with the eigenvector. So what it will do is, if you multiply this with the eigenvector, what it will be doing, like this will scale, but the direction of that will remain the same. This will
Yeah.
scale by value what? By value of eigenvalue of that eigenvector. The corresponding eigenvalue of that eigenvector, it will scale. So what we are doing is, like, we are removing that eigenvalue itself from here.
Yeah,
If you are
that's what
getting
I'm
the
saying.
point.
The magnitude information will be lost.
Yes, yes, yes. So magnitude
We can
information will.
find the component or the direction, but we'll lose the amplitude.
Yeah, yeah, yeah. So
Okay.
anyways, the amplitude will be like normalized. If it is single element, it will like will be losing information, but the total vector amplitude will be anyways normalized. So yeah, if you're getting the point, as in if you multiply a unitary with a normalized vector, or even if it is not non-normalized, the norm of that vector will always be preserved by that unitary what you're multiplying it with. So for preserving that norm, the constraint should be imposed is what? The rows and the columns should be orthonormal to each other. Only then any vector, if you multiply with that unitary matrix, the norm of that vector will be preserved. So what you are saying is correct. If you multiply the magnitudes with that norm, then at the end, what will be getting? That change in magnitudes of the norms will be getting, right? We have to avoid that. Hence, we are removing that magnitude itself, that eigenvalue matrix itself from this picture. So what you said is correct, true. Yeah. Okay. So moving on, uh, this one thing I'd like to highlight here. In a unitary matrix, if you consider a unitary matrix, those unitary matrix can be written in terms of sine theta, cos theta, and like other trigonometric functions. So whatever unitary matrix you have, that is nothing but like a function of the quantum angles. Whatever unitary gates also you have, U3 unitary gate and C0 gate can reproduce any unitary. So if you multiply this or tensor product this, what end product will be giving, like getting in terms of element form, are nothing but functions of the quantum angles, are the those are the parameters of those U3 gates, whatever you are used, because C0 gate is fixed. So this parameters of theta, phi and psi, for many number of qubits you'll be getting. And if it is an n cross n unitary matrix, you'll be getting this independent parameters. So this number of quantum angles you are required to construct that unitary matrix. Yeah, those are all the details I wanted to give here. Now, so coming to the phase encoding, like what exactly is a phase? So we have just three more encodings. I'll not bore you with the theory more. Like after this three encodings, we'll directly move on with the code, and just like I have this one more slide, like this one more slide. So in this, there are two common final tasks that we want to discuss, and this also you want to like implement. So what these tasks are, like I'll discuss. Yeah, we'll close in just now it's 9:30, right? We'll try to close it before 10:30 if possible. Yeah. So like if this three encodings are like two encodings are like you're aware about that, like we can move on with like complete their code simultaneously. So we'll not be bored with the theory first. So this is nothing but we have taken an like MNIST data set, and we have like first extracted like whatever discussed, like we have first converted that analog image into a digital kind of setting. So this is the directory, like from here. So this is my personal directory. You have to change it first of all, and then we have used IDX to NumPy library. So what we'll be getting here are the NumPy formats of all the images, as in the digital formats in terms of numbers. And then we have separated it for particular zero labels. How many images are there? We have tried to like we have separated it here as per the list. Then imagine first let's say 5,600 and something like images will be of zero. Then the second set will be one, because the data set was mixed, like the numbers were random. So we have done that first year. Then the remaining code is nothing but if you go through, it's self-explanatory. What we've done here is nothing but we have whatever shape like we have of a conventional MNIST data set is nothing but 28 cross 20 matrix. So we have tried to resize it here into 32 cross 32 setting, because we are under the unitary constraint, as in the qubit constraint, the qubit dimensionality constraint. The two, like if you'll vary the n from 1 to let's say 5, you will just get 32, you will not get 28. So that's why you have to convert that into 32 cross 32 pixels, as in 1024 pixels. So after that, like like for each like a list of like image in the particular class, like we have converted that into so first we are resized, then we are converted into array, then last will be like flattening. So here we have flattened. So this is nothing but our amplitude encoding. So this is nothing but, so you can remove this as well. You can directly put an for loop here, and you can directly put an array here. That will also be fine. But this is not an efficient code. What you are trying to do is like complete the code first. Efficiency can be done for the later set of intents. So please bear with us. So like this will be our first list, and like this np, what you are doing, np.linearity.norm. So what we're dividing here with, this is nothing but the norm of the whole vector of that respective vector, and we are trying to like we have amplitude encoded that vector. So what exactly is the amplitude encoding? We have discussed in this year, like a square plus b square equal to 1. So if it is a like a higher qubit vector, a higher dimensional vector, in this case it is a 10 qubit vector for cross like 1024 vector. So that will be a 10 qubit vector. State you will get here is nothing but a 0000 up to so on up to 10 qubits. Then like can write 2 raised to 10 states, right? If you're getting the point. So the first state will be like the first position. The second state, like second state, what you've written in that 000 last position 1, that will be 1 at this position, remaining all 0. If you're getting the point. So after that addition, what we'll get is our vector. So this vector will get AB na, that vector will get 1024 vector. So this is nothing but our quantum state is still written in vector form, if you're getting the point. So like this is our vector, like and then for like having this dimension, like balancing of the data set exactly, you can ignore this step as well. But for having the balancing of the data set per label, like if you want to have the same images, so this is done, the indexing is done up to 5000, and then like all the amplitude encoded state vectors are appended. So this you'll get as a number, so it is just reshaped at the end. So like these are your tasks. So right now we have dealt with the first block from here. So this first block is done. So since this is amplitude encoding, we are not multiplying with the Hadamard gate. So amplitude encoding block is done for now. This is your task, feature extraction for linearization. So what exactly is so this again is a block that again contains a theory. So at least I have discussed 3 in this document. So, but the document, since it is not in printed form, actually wanted to give the document only. So like will I don't know, it's not possible for us to like type it all and give to you. But these are like 3 architectures we had come to conclusion for converting nonlinear linearization of the data set. Just give me a sec. So this, yeah, product, and yeah, so this from here. So linearization of the input vectors approach. So there is like, this is one of the approaches using dot product. And so if you are aware of support vector machines, you will be aware of this approach. So what exactly this is, this does is takes the dot product of each vector with this like neighboring vector or all the vectors, remaining all the vectors in the training data set, and then get that kernel vector matrix, that kernel matrix, which is nothing but a Hermitian matrix. And then that matrix, if you put on some like a Taylor series, or if you put on like a RBF kernel function, what you're when you're putting in that function are nothing but the elements of that matrices. And then if you'll fine tune that hyper parameters, the gamma parameter and the C parameter of that RBF kernel, or are like Taylor series, like we have given you one Taylor series implementation. So that is also one of the like technique of linearization of the data set. So if you look into today only, I think like I have posted it, the code for that, like using SVM, like QI SVM for linearization. So you can go through that code as well. So this is like one of the approaches. We will not get the time to discuss this in detail, but like you have to explore this part on your own. So your neural network, what exactly it does is, at the end, if you look into, if you have 10 classes, so what exactly at end it does is multiply. There will be a linear matrix layer at the end. So if you have neural networks and all, like you're multiplying, there will be a weight matrix at the end, like whatever output neurons you require. So that scaling down is nothing but linearization, right? So before that layer, linear that before so if you're getting the point exactly, so this suppose our input, yeah, input layer of the neurons. This is our hidden layer. And for simplicity, let's consider we have like only 2 hidden layers. Okay, and we have like let's say 3 classes what we require at the output. Okay, so this will be a fully connected neural network, so there will be lines here all the way. So what it will contain is nothing but a weight, a bias, and an activation function in this neuron, a weight activation, a bias function in this neuron. So before this, so as in the last layer will be a linear matrix layer, and there will be an activation function in the sense of sigmoid after this, right? Sigmoid. So before that, it will just be a weight matrix multiplication to get it right. Just a weight matrix multiplication if you're getting. So what it will be a 3x3 matrix. You'll be getting a 3x3 matrix here. So this matrix is nothing but the end. So before this, what we'll be getting a linearized version of our entire like data set. So whatever data set you're given here, this is the linearized version of that. That's what is entails at the end. So sigmoid, what it does is nothing but it converts in the form of 0 and like this e raised to if it is Sopnak function, this will be nothing but e raised to some summation of e raised to that I don't remember the exact equation. Some equation is there, but anyways, this is a Sopnak function for multiple classes, and then there is a sigmoid function for 2 classes. So this mapping. So this is why I'm explaining this in detail, because you have to. This is your second common task. Whatever vectors you are getting from here, you have to plot a 2D plot. 2D plot of that as in mapping. So from input vector mapping to this vector mapping will give us what exactly is the function required for linearizing the input vector to this stage. So I have like we have given you the code for SVM approach in which we have plotted a 2D plot. That is what we're expecting for every neural net architecture, network architecture. For MU datasets it's also fine. So like moving on, so I just given a gist of what exactly feature extraction will be expecting from you guys. So you can like implement any like neural network or any like linearization approach. But if you can explain or if you can plot this plot, if not if you have to plot this plot, because this function will be giving us the explainability of the neural network. So what exactly is the function that neural network is mapping to make it a linear data set, if you're getting them. So and after that, like at the end, we can apply unitary here itself. So we can, instead of using a weight matrix, we can apply our own unitary. So that is our QML thought process. Because a unitary itself segregates linearly, we cannot put in a like a non-linear data set for our architecture, limited to architecture. There are many other architectures that we can like we have tried to like give you the code of. So those are following this this like non-linearization approaches in the quantum setting itself. But this is our first architecture. So moving on. So like we'll be expecting you to implement this from here, so you can go through this whatever is written. So 5 implementation, as in using dot product and universal kernel function, just the names of that is written here. So what approaches you can follow, and then yeah. So this again, this 7 point what is written here, right? We were thinking of giving it the document first, and then you'll be understanding what the general rules of creating this quantum inspired analogs are. Then you'll be trying to implement. But like if you're not understanding anything, you can message us, and like we can go through the details of that. But for now, like let's move on. First is your first task is this one. Second task is like this target vectors. So okay, if you look into this, now we have been discussing this, right? Input vectors, output vectors. But what are output vectors exactly? We have not discussed that. So like here, so what exactly are the output vectors here? We are not discussed that till now. So these output vectors are nothing but your class labels. Nothing but these output vectors, those will be your target vectors. Okay, if you're getting the point. So if it is a class, let's say you have 10 class labels. So for every class label, you can convert that into a target vector. Okay, not here. This target vector or target vector. So every class label here. So if it is class 0, what you can do is convert that corresponding position into 1 and remaining all zeros. If it is like class 1, what you can do, if it is a 1024 matrix, you can divide that into number of classes minus 1 here, and then you'll get the spacing between two ones. So this like 113 spacing is there, right? So for first class label, you'll put in for second class label, you'll put one at 226. For third class label, you'll put in one at like corresponding 313 position, and so on up till the last class level. So that will be your target vector for this case, and you'll repeat this target vectors for the number of data set points, like whatever you have. If it is 50,000 data sets, we already converted that into 5,000 per label. Then you'll be getting that those 50,000 like target vector states, and those will form those matrix. So what you have discussed, output and input vector matrix. So this is, since this is a supervised approach, you're already having the class labels for it. So like so you'll be getting this matrix, and then you have this techniques for converting it into unitary matrix. So hope this is clear, and this is your research point. So whatever target states combined we have implemented here, it is like our own research, because this gives the best result for now. But this is your own, like even if it is for single data point in the particular class, even if the target vector is different is also fine, but find the target vectors such that you need not linearize the data set. This will give you the optimum like result, if you're getting the point. As in this is limited to per class label, right? All the 5,000 will have one at the first and remaining all zeros. But like it can so happen like there will be a set of, like if you represent all the data points in a circle, there will be a set of like data points that will represent this circle, as in that circle clustering kind of setting. There will be a second class representing that. So all the target vectors in that circle like can be taken here, as in like per class you can take a different target vector as well. And if, what like thought process was here is like all the target vectors to be maximally separated, those should be orthonormal to each other. So that's why it's taken like this. You can try like implementing any target vectors per class level as per your thought process, as per your logic, and try to increase the accuracy. Okay. Hope this is clear.
Uh, yeah. Oh, yes, that is clear. Can you show me that target vector which you have written?
Separation approach. Yeah.
Ah, yeah, these vectors.
Yeah.
Can you just tell me? There are only very few target vectors, but what are those many values in rows and many values in columns?
Okay, I think like we missed the explanation. So I'm moving fast. I know the point, but like so that's just why recording was beneficial here, because you could try to read the recording again. So what I was trying to tell here basically is like this 5,000 first vectors what you're trying to put here, right? This 5,000 first vectors. All
Hmm.
the vectors first label first element is nothing but one, and the remaining all are zeros.
Yes,
Yeah,
but
and
why
what
did
your
we do that?
research.
Like,
Yeah, because these will be maximally separated, and this is trial and error approach. As in, we found that this first the logic was this should be maximally separated. We tried various orthonormal 10 states, and then we repeated that for 5,000, but the implementation result was not that good. So what we did is like implemented this as our target stage. So you can try researching this, and then instead of using the feature extraction, you can directly change this only. Try changing this like for various values, and like try increasing the accuracy of classification. So yeah, so this is our
okay,
first implementation. Yeah, this class customer like reduce Elrond plateau you can remove from the code, but this is kept for decreasing the learning rate to a value greater than 10 raised to minus 6, because the value limited to the RL reduce RL plateau from the like PyTorch library limited to 1 e to the minus 6. So for that, this code is written, but you can remove that, and this is our class, particular class. So what we are trying to find is a matrix. So this matrix is written, and this is without any bias. So bias has false value in it. And so this, what we are doing just is nothing but multiplying this matrix to our vector. So input vector is nothing but the x, and this is our loss function. So the basic ML pipeline, if you look into, nothing but first what you do design or implement is nothing but a class in that which it will be a forward method, a self method, a forward method, or an initial decorator here, and the forward method here, and then there will be a loss function that you want to minimize. So this loss function is incorporated here, which is nothing but the RSME loss between the output and our target vectors. We already have implemented the target vectors. Output what will get it from here, unity into X, and this is nothing but our three matrices. So as in two matrices, what we are trying to reduce. So U into U dagger is equal to I, U dagger into U is equal to I. These are nothing but the two orthonormal losses, and these are nothing but the identity implementation, and this is nothing but the so why the transpose dot transpose is taken and not dot conjugate dot transpose is taken here, because we are taking it in real space. Like you can convert the code, you can put in here C float, and this is already complex, but this warning it's getting ignored and it's converting into real space only. But you can try like implementing a complex version of the unitary itself. But since our all like input and output target vectors are all real spaces, the second thing also there is like important point. If you go to, read into this now, the target vectors also can be entangled. So those like thing we are not like explored yet. As in 10 qubit entanglement state also can be, if you want to showcase that like the kind of thinking here, normalized entangled like state, does it give any advantage? So that can also be explored. Like you can put in a complex state also here. You can put in 0.707 plus 0.707 J. So that can also be researched here. Like there are many points of research. This is open to research, and this is also open to research. So okay, fine. And then this is nothing but the training loop. So for here it will be the loss function will be reduced, the back propagation will happen in this stage, and this step will nothing but implement that optimization, or this per step you want to implement some kind of scheduler, then it will implement this we have implemented a custom scheduler for that. Okay, this will be our first method, and then after getting that unitary, you are multiplying that unitary with our input vectors, and then you will be getting our output vectors. This will be by ML method. If you want to implement the SOD method, the SOD method is implemented here. So like this is nothing but our M matrix, as in the the non-unitary matrix what we have discussed. So since this is an what we are discussing is just single vector, so this get output into bra input we are doing, right? So here we are doing all the transpose to match the numbers exactly. So if you look into this target array, this target array is nothing but 50,000 cross 1024. If you take a transpose of that, 50,000 cross 1024, and before what is the X pseudo inverse is nothing but, since you're porting that state from this side to this side, the input state, so you have to take the inverse of that matrix. So yeah, so you have to take inverse of that matrix, and this will be your array here. And to again the match the dimension, you're taking the transpose there, and then of that you have taken SOD decomposition and multiplied these two matrices to get your orthonormal matrix or the unitary matrix here, and that's it. And this is nothing but the verification of the orthonormality, whether it is orthonormal or not, based on the same U dagger is equal to I, U dagger into U is equal to I. And again the accuracy is computed like in unitary into input vectors equal to output vectors. That output vectors minus like target vectors, what those values, and the RSM of that is calculated here. Okay. And if you look into both methods, the RSM value of the ML method is lesser, but the accuracy of this method usually with followed by NN is better. So like SVD is nothing but a more accurate approach than ML. But so again, this implementation is done whatever unitary we got by SVD method. So if you look into, if you just change here from orthonormal matrix to just return M, that will give you the non-unitary matrix. Okay. Yeah. Now moving on, same what you have done on the upside, right? Same thing we are doing with the test data. That was the train data, this was done with the test data. So this again same images label we have taken, we have converted that into NumPy format, a digital format, then we again reshaped it to 30 cross 32, and then we have normalized it, we have multiplied it with our trained unitary here, and that's it. That's all the implementation. So whenever you'll implement the feature extraction, you'll change you'll transform the input vectors here, right? So those feature extraction techniques can be any neural network, can be any Taylor series, can be any SVM approach, or any you can increase the dimension of the vector as well. So after that, those will form your input vectors here. So after feature extraction will be an input vectors. So first step of research is, before going into feature vector, change this to whatever you desire, or go through read research papers. This is an OL implementation, so you'll not find this kind of setting in any research paper. What we'll try to look for is how we'll get this exactly separated state or different separated state. Those are maximally separated from each other. As in, if you draw circle, those circles should be maximally separated from each other. So orthonormal is one of the conditions. Like you can implement or try to think another condition. After this, when this research is done, move on with the feature extraction implementation. That's it. Okay. Now, like moving on after this, like hope this is clear. So this, if it is clear now, even if I explain the theory of all the encodings, remaining implementations are all like here you can try to implement QR decomposition as well. So instead of just SVD, what you can do is same thing, same code. Instead of this, what you can do is just apply torch.linearity.qr, this M. If you'll do, you'll get if you'll remove this S, you'll just get Q and R matrices. That Q will nothing but your orthonormal matrix. So that's just that change you have to do. Yeah. Okay. Now, now this is again linearization of the data set. As in, if you look into MNIST data set, you can go through what exactly is written here. So like we have only written here, this is relevant to your task, so you can go through. Now, and this implementation, what basically it tells is what is the degree of your data set. So like if you are applying SVM, so that SVM uses has a polynomial kernel in it. As in, after getting that kernel matrix, after getting this is an inbuilt method. So I cannot show exactly where the kernel matrix is used, but this is our input data, our test data, whatever after the no, this is before transformation by the unit operation. And then this is a scalar, like we have scaled the data using the standard in the standard deviation and the like mean and the standard deviation as 0 and 1, taking that and we have scaled it using standard scalar. And we have used the kernel as a polynomial kernel, and what exactly at what degree it use the highest accuracy, that degree of the data set will be a linearizing degree of the data set, if you're getting the point. As in, I can show you the plot as well. um, so this it's taking time. Okay, yeah, it's taking time. Bear with me. Okay, yeah. So, what the thought process for implementing this second point was, like, after transformation of the, so, okay, sorry for this. I have not changed these labels. So this should be changed from input state vectors to our after transformation of the unitary, what exactly our output vectors are. Those need to be changed here. And then, is there any degree change the data set? That's what we were trying to research here, but there isn't any change in the degree of the dataset. The degree of the dataset remains the same. Degree of the dataset here means that the degree at which the classification accuracy by the SVM method becomes maximum. That is nothing but the degree of the dataset. So even if you like that, that is why we are using polynomial equation here. So like if you look into details of that SVM code, what you have shared, right? That exactly details about what exactly degree of the dataset means. Yeah, means what degree of the data set or what polynomial transformation of what degree or to implement on the data set to make it linear. That forms as the exact definition of degree of the data set. So this has been opened. So if you look into this increases up till this point. So this is nothing but 3 is nothing but the degree of the data set. This has increased. So 3 for MNE data set is the degree by SVM method, SVM polynomial method, and 3 in general sense can be taken as degree of the data set. So why it has not become 100%? Because we are not fine tune the parameters. There might be some outliers in the data. The data might be noisy. That's why it's not exactly 100, but a degree 3 polynomial can exactly segregate a MNIST dataset. That is why MNIST dataset is not taken as a very complex dataset, because a degree 3 polynomial equation can itself become make it linearized. So since we are in the research stage, at the start we have taken MNIST dataset. So yeah, for more complex model, the degree of the dataset can be infinite. as in if you look into take a simple function e raised to x. If you write a Taylor series expansion of that, that will be infinite, right? As in degree will be infinite in that case. But the remaining the remaining terms in the Taylor series can be truncated down, because those are divided by a large factor of those factorials. So those can be ignored, and then only truncated Taylor series can approximate our original function. So that was our thought process for implementing the SVM by Taylor series approach, which we have said the code block for. Okay, yeah. So this is done. Like second, this is our unitary encoding task 2. Same things are written here. We just only change the name. Baki the tasks are the same. You have to so the main difference from this embedded encoding to unitary encoding here is we have implemented or multiplied that Hadamard transformation of that state with our unitary with our unitary encoding encoded matrices. So this is nothing but the previous steps itself. So now if you look into what we are playing with here is nothing but vectors, as in vectors we are transforming, right? But the image matrix what we are getting is nothing but 32 cross 32 the start. So if you look into here, we have reshaped it to 64 cross 64. Why? Because here the computational requirement after multiplying our input vector with this setting is nothing but what you will get is 64 cross 1 vector, if you are getting the point. So 64 cross 1 vector is nothing but computationally very like less requirement for that. If you look into previous example, why 64 cross 64 here, because it takes into account 4096. So after flattening that, but here you did not need to flatten here, because you're multiplying the input vector first with the Hadamard gate. The superposed state is that multiplied with our unitary encoded matrix. So this is nothing but the previous procedure what we have followed. After that, this is again okay, this procedure you can ignore. So what through our implementations we have found that even if this is ignored, like if you're not normalizing that matrix, okay, this step needs to be done. So we are normalizing here first, so this step needs to be done here. So divided by max, this is one of the process of normalization. Second is np.lineage.norm you can put in, and then you can put in furrow there. So that implementation also will normalize the matrix. So this implementation needs to be done. And then there are like various approaches we have discussed, right? So first is our SVD decomposition. First is our unitary encoding, then is our SVD decomposition, QR decomposition, ML method, ABN of making that matrix unitary. So here we have implemented our unitary encoding approach. So we have directly written the imported penilin as QML, and penilin QML directly has a function or attribute in it of block encode. So that block encode we are directly utilized here. It directly does the mathematical transformation what we discussed. It directly block encodes are normalized unitary, or even if it is not normalized, it directly encodes. It first makes it normalized and then encodes it into to make it a S matrix, which is nothing but our unitary matrix. So this unitary matrix we appended. So what change needs to be done here? Nothing but if you look into digit 0 needs to be float 64. If it is float 32, the Qiskit doesn't accept it as a unitary operator, because it becomes like if you look into u into u dagger minus I, that will be 1e to the minus 6. So those are above 10, 1e to the minus 10. Those are only accepted as a unitary operators in our Qiskit kind of setting. So that is why float 64 is needed for this code. But since it is a quantum inspired approach, so you can put in float 32 as well, not an issue. So after encoding, you'll get a 128 cross 128 matrix, and similar done for one. So again, efficiency is not taken into consideration here. One can do all this step like in just one code block instead of doing 1, 2, 3. Okay. This is the second step, like second method. This is commented out. You can uncomment it and you can run. You can also try implementing SVD here. Similar approach. Again, you have to convert it into SVD and then follow the similar steps. Okay, and now we have multiplied that with the Hadamard gate. So this first we have like taken the Hadamard gate, multiplied that Hadamard gate or Kronecker producted, NP or Kronecker producted that to get our for 128 if you convert that into number of qubits, those will be I think 7 qubits. So those you have multiplied that with 7 times here, because you have multiplied that already first. You're like multiplying it 6 times here. Kronecker product, that result would be 120 cross 1, and then you're multiplying that with the input, as in the input is what here, the ground state of the qubit. The ground state of the qubit is nothing but we assumed it to be 000 and an actual quantum computer also to be 000 as in Kate notation form. So if we convert that into vector form, the first element of that will be 1 and the remaining all will be zeros. And then you multiply that with whatever unit you have gotten, and then it will be r this we have come till here, right? The unitary hard number we have multiplied, we have come till this line, the vectors what you have gotten. Then after this, same implementation, you can implement unitary of separation. Before this implementation, there will be a feature block. So you have to implement that feature block here first. Then after that, like you have to change from input state vector to your feature encoded state vector. Before that, you can experiment with these target vectors, and that's it. The implementation remains the same. Only thing is we can try increasing here to 256 as well, because here the matrix doesn't come into picture. Here we are taking the vectors, because this vectors are all 120 across 120 across 1 only, right? If you look into the previous amplitude encoding, the image matrix is converted into vector. Here the image matrix multiplied by vectors, so that image matrix, if it is n cross n, the vector will be just n cross 1. So that's why the dimensionality can be increased. If you're getting the point, you can increase that to 1024 cross 1024 matrices as well, but it will cause again cause this computation error as well. If you have the better computer, better pieces, you can try that. Anyways, yeah. So same thing is done for test data set here. So this code needs to be implemented after your feature extraction, but it is written here. Anyway, so same tasks are written here. You can go through these tasks. This is nothing but after unitary implementation, this is the multiplication of that unitary. And again, so this does unitary encoding change the degree of data set? That was the point of this implementation. So it does not, because it's a linear kind of encoding. But it changed the graph shape if you look into, and it changed the accuracy as well, because you are superposing the image matrices here, image matrices element here. So that's why it's changing the degree of the data set here. So from 98, the previously amplitude encoding, it's changed from 8 to 92. So yeah. And after multiplying it for the unitary of separation, does it change the degree of the data set? So no, it doesn't. It still remains the same. The maximum occurs somewhere around 3 degrees. So yeah. So here it has so it's 3. So if you look into this graph carefully, S is 3. I don't know, there might be some issue here. But for all the implementations, we have found the degree of data set between 2 and 3. So it may happen for some implementation it's 2, some implementation it's 3, but mostly it is 3. Yeah. So moving on, we will not look into the codes further. We'll just explain the theory, and remaining implementations are all same, because unitary encoding what you got now, that was the only differentiating factor. We have used Hadamard there. Remaining are same. If you know the theory, you can easily implement it. So theory is nothing but this. Phase encoding is what is exactly phase encoding means. So this e raised to I lambda, this lambda is nothing but the phase of our quantum this state, right? This e raised to I lambda. So lambda is nothing but the phase. So this you can implement or encode our quantum our classical data set into this e raised to I lambda kind of setting. So this e raised to I lambda, as in the lambda can be encoded as a classical data set, and then you can perform e raised to I lambda on that, and that will be our pixel value, and the pixel position remains the same. So for first procedure, what we'll do is convert the analog to digital matrix. Then digital matrix will flatten out. Then what we'll do is take the element and then multiply it with the range. So this is nothing but a radian form of 360 degrees. So multiplying with that and dividing by the maximum value of the pixel, it ranges to 255 only. So this element, what we're doing is first normalizing and then converting into plus minus 360 degree range. So once we get that angle, we can directly put it in this equation: cos lambda minus I sin lambda, or cos lambda plus I sin lambda. That is also point of research. You can take any kind of phase encoding here. And once after phase encoding, the architecture remains the same. Angle encoding is another point of research. Here in angle encoding, you can implement this all encodings: e raised to I theta, cos theta plus I sin theta, cos theta sin theta, any trigonometric function, any hyperbolic function, any inverse of hyperbolic function, any inverse of a trigonometric function can be implemented, can be researched here. The point remains the same. You have to linearize the data set, and you have to import that encoded state onto the quantum computer. But since it's a spread approach, we are not taking any unitaries matrix multiplication and then not converting that or transplanting that unitary matrix into our unitary gates and C0 gates, but the implementation remains the same. So in binary encoding, what we're doing is, so this is the actual quantum computer encoding. If you look into Gross algorithm, Shor's algorithm, for encoding the numbers, we are converting those into binary format, zeros and one format. So how to convert that is nothing but pixel positions are first converted into binary format. So like conversion from of 0 to 255 to binary. So 255 equivalent binary, you will get like 8 binaries. 255 is nothing but like 1111 all ones, right? So like you can write the binary. You can also do a Google search of that. You can also like have you have also studied the method for that in, I think, your undergrad or your 10th and 11th standard, like how to convert that given a decimal number into a binary form. So that is what we're doing here, a binary form. And then what we're doing is multiplying that with the corresponding binary state, binary encoding, tensor producting that. So this tensor producting will give us our binary encoding. So if you look into the implementation has a quantized version of our pixel, like of our image, because due to the computational limit. So if it is 0 to 255, we have first divided it by 255 all the images, like all the images. So it will be in the range of 0 to 16, and those 0 to 16 we have taken integers of that, as in this is the form of quantization to reduce the computational dependency. And then like we have limited like it to just number of qubits we are trying to reduce here basically. So if it is 0 to 255, then the number of like binary elements what you'll get from like 255 will be a large number compared to 16. That is what we are trying to reduce here. So this is our encoding, the final. So binary of I, as in the pixel values, tensor protected with the pixel position, what it is. And yeah, so you can try go through the code as well. And again, code like after this also the normalization step should be implemented, because it's not normalized after this. Okay. Coming to the novel density matrix encoding, these are all the vector kind of settings apart from unitary matrix, and this is only apart from this. This is only a matrix kind of encoding, a quantum matrix encoding, and this cannot be actually ported. So this is only implemented in an inspired approach. Yeah. So it has like 5-6 methods. So bear with me, and then we'll close this session, or like after this. Okay. So before going to novel density matrix encoding, we'll first like close this session. So there's common final task 1 and 2. So what exactly those are? We have touched upon what exactly interpretability and explainability of every NN-ML architecture is, as in like we have touched upon the topic, we have drawn the neural network diagram for that, and before the last layer, whatever the vector is, that is nothing but you have to plot in 2D kind of setting. We have already given a code for that in terms of SVM. So like you can go through that. So what exactly is expected here is a 2D plot, and second thing is you can do a hand calculation as well. Take a short example, do a hand calculation, plot it using matplotlib into Python. Like yeah, that is also fine. But what we require here is like okay, but then you have to do the back propagation also by hand for that small data set what you have taken. So instead of that, better to compute it using Python library, like Python libraries itself, rather than doing it by hand. And the last layer, whatever vectors you are getting, try to like so whatever last layer vectors you're getting, I'll try to like walk you through what exactly we'll be expecting. Try to form like a Taylor series expansion relation between the input vectors what you're getting to the output vectors before the last layer. So that last layer, hidden layer, should be same with the input layers what you're trying to provide in that neural, this Taylor series approach. Or you can follow this symbolic computation approach using SciPy library, but it will be limited like not SciPy library, simple library, sorry. Simple library. It's a like you can say a sisterly or brotherly like library of NumPy library, which uses symbolic representation. So what weight matrices we are doing, right? So that those weight matrices can be written in terms of like a variable kind of setting, and but this is very slow library, so it will be only used for a limited set of like dimensionality of the vector. It cannot be used above that. So yeah, but you have to research this. And second is this video. So you can try watching this video as well. This is just a short video of 20-30 minutes. He has clearly explained a concept, how does the additions of the activation functions takes place in the neuron to approximate approximate a function of the data set to exactly segregate the data set. So yeah, so this is the second task. The first talk, what we'll be expecting you is the main thing. So we have discussing only the classification approaches using QML setting only. So this is what our like a thought process here is. So if you have been like if you're aware of LLM, what exactly LLM is, it's trying to predict the next word. So if let's say I am at let's say Mumbai, so I am at Mumbai. If it is like if the neural network or the LLM model has been trained on, I am at. So Mumbai, if it is trying to predict the next word, so that next word will have certain probability in the final classification. Like yeah, I'll have to write it here. What we are trying to do here basically is uh, we'll not go into details of what exactly transformers is, or how exactly it does the modeling. We will ask you to write the report on that. You already know that, but the state of the art is continuously progressing. So you can take a DeepSeek, you can take Olama, you can write a research report on that. That will be a secondary task, but this will be a primary task for you. So let's say we are importing vectors in it. So first what you'll provide first for training, what we'll do is you'll have this like you will have corpus like corpses of this data, as in you'll take it from internet. So for this specific task, we are limiting it to maybe 1 million data set. You can like limit that data set as well as per your computational power. But what we'll be expecting from you is here is, so I will be converted to a vector, a text vector kind of setting, will be limited to a certain dimension, let's say n cross 1. Similarly, M will be limited to certain like text embedding will be n cross 1. At will be limited to certain n cross 1 setting, right? So we'll be using some open AI model or some already existing text to like vector embedding models. You did not research in this. That will control the dimensionality of I, M. And what it will do is it will like give the contextual meaning of I in the sentence, and you can form a word like a vector of that. So, but first, what we'll be expecting is you are just given I. Now, if the our LLM classification model is trained I, then it should output what? M, right? It should output M. So what essentially this LLM model does is classifies. It classifies as in what? If you have a classification here of 50,000 data, 50,000 cross one vector, let's say all your vocabulary will be controlled by this 50,000 cross one, as in it can be tokens as well. We have taken all the words here. It can be tokens as well. You can take it as a characters as well of the alphabet. That will be a even clearer thing. So the number 0, 1, 2, 3 directly you can take, but this will be a computationally exhaustive thing. Not here, I think so. You can try. This is a research field, so you can try. So up till 9, and you can take A, B, C, D as the like your characters here as the output classification. You can say tokens. These are nothing but your tokens. What will be classifying your output probabilities to. So let's say I'm given an I. So if M is present is fine, or there will be an A present here. So what it will do is it will classify this A as correct, as in A will have the highest probability, and then it will again take A here, embed A here. It will pass this again into the same LLM model. So how you have to change the vector in this case? So this I will be a vector. So for start, what you can do is add, just concatenate this A here, normalize it, pass through the LLM model, get M as the output. This is in terms of character setting, but you can try experimenting here with any kind of token words. So if you look into ChatGPT as 50,000 cross one, other models have limited, like BERT has other tokens at the output. But this is our general sense. So I know like the classification models are not like exactly able to understand the contextual meanings of these words, but what we're trying to do is exactly that. We're trying to concatenate the words in text vector format. After concatenation, we're trying to classify. So you'll have to explore the difference between a discriminative approach and generative approach. What we're trying to follow is a discriminative approach here for constructing an LLM model. That will be our sole IP if it works out, I think so. Based on this, if the model complexity is high enough, it will work out. but you can try implementing it for maybe 1 million data set. Hope this is clear. I can like we can have a later in-depth discussion about this. I can dive into depths of what exactly transformer architecture is, but like will not be okay. You can ask questions. If you're interested, we can have a session on that as well. But for now, like today's meet is already over time, so we'll try to limit this. Hope this is clear. What you are expecting, you can go through this reading as well. And if you're not understanding something, you can ping us on Slack. So, and this is our last task. So you can try implementing LLM using conventional transformers. I think some of you already done this. Not LLMs, but you have implemented text to vector embeddings and train transformers on it. So this is an extended version of that. And you can try writing report on DeepSeek Olama based on the time constraints whatever you have. So these are all the common like tasks. If you have any questions, you can ask. Yeah.
Uh, 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 actually, everything was
Yes.
actually so good. The only one doubt is regarding what is the task like. The last two are the tasks, and earlier already you have showed many scripts. What are those? Again, you want us to implement those and do right. So,
Yeah.
uh,
So these are all the common tasks. So beg your pardon, like I'm not able to see the screen now. So can you please tell us your name?
Gopal, Sai.
Gopal. So, hi, Gopal. So, like, what exactly previous six encoding does is like it forms a basis of all the individual tasks given to you. So, those will form the basis. I think what those
Mm-hmm.
encodings are, what exactly is the unity of separation. So, once that concept is clear cut in your head, like you can try to go through the implementations, what you have done, like individually, and assign the tasks to you. Those are your individual tasks. So, this what the
Okay,
like main goal of today's session was to get those things into like a concept into your heart clearly, and then like do implementation in those tasks, and then use those implementations in the individual tasks that will be given to you, or those have already been given to you, and these are the common tasks for all interns.
okay, got it, got it, got it.
Yeah. So moving on. So hope this is all clear. The last point we'll like to discuss today is novel density matrix encoding. So this has like many implementations, and this like so we'll directly go through it via code only. It will be easier, I think, and not return that exclusively in yeah. So this is itself, right? It's written here. So six types of novel density matrix encodings are implemented. So this is like just so what by the name. What exactly the density matrix, the mathematical property of that is nothing but it is Hermitian matrix. And the second mathematical property is it is not an observable. So as in it doesn't obey the von Neumann equation. So what are observable, like to call it as a quantum observable, you need to satisfy the von Neumann equation. So it's nothing but a reverse form of Schrodinger equation itself. If you look into, you can Google it, you can go through documents as well. So if it satisfies that equation, then it is an observable. So this is not an observable, and we are trying to put a mathematical construct of Hermitianity on our input classical dataset matrix. So that is what we're trying to do here. So this is one of the approach. 1 plus a like okay, first approach is nothing but a into a transpose by 2, or if it is a complex like matrix, you can put a conjugate here by 2. This is nothing but Hermitian constant. Second constant is this a plus a transpose by 2. This is the like basic massive we have been dealing with 11 and 12. So this is one. Like the second thing is this, as in if you convert those, we already discussed amplitude encoding. If you amplitude encode our image data, a classical matrix, flatten it, normalize it, then amplitude encode it. Amplitude encode means this, you will put it here, outer product it. You already discussed outer product in the warming session. Outer product with our input normalized state vector, that will result in a Hermitian matrix. Those will form as a density matrix for that particular data set, but this will be computationally exhaustive. So after this will be like taking a single constructing a single like per class only single matrix that can be done via this. So this pi, what it will try to do is it will try to like approximate the probability distribution of per class. What we are trying to do in ML models itself is like per class we are trying to assume that all the like data points in that particular class has the same probability distribution. But here what we're trying to do is we are trying to provide probability amplitude associated, and then we are trying to sum and construct a single output of the training data, a single image matrix. So, but since like we have implemented it for average kind of setting, as in we have divided it by 1 upon 5,000, so this will give average accuracy result that has been proved. It gives 67% accuracy. The fifth procedure is nothing but like other novel procedures of getting a Hermitian matrix. So this is nothing but other procedure, as in if you look into unitary constraint, u is equal to e raised to minus I h t by h cross. That is the equal matrix relation. So in that relation, that instead of Hamiltonian our density matrix, and construct the unitary encoding by or other discussed methods, you can get a Hermitian matrix from that as well. Yeah, and that has been implemented. And then unitary encoding, you can get it from many ways. And for getting a Hermitian matrix, you can put in this. But what exactly after implementation, it has been observed that like even the floating point of 64, the matrix doesn't become Hermitian because the scaling of that is nothing but in terms of 10 raised to minus 12, minus 13, minus 14. So it loses information because the computer stores in terms of floating point numbers. So the matrix after this transformation doesn't become a Hermitian matrix. So you can try researching in that how to make it as a Hermitian matrix. So after this, you can add one more layer like of A into A transpose by 2. So that makes it as a Hermitian matrix. And yeah, so this is nothing but the start. The same thing, pre-processing. Here, create Hamiltonian, a function is created. Like this is the first type. So what we are doing here is nothing but vector. Like we are converting that into vector setting, and then normalizing that, and then that vector we can try to multiply with itself in a transpose form by 2. That will result in a okay, yeah, sorry. So this what we're done at here is nothing but reshaped it here. So this can be ignored, no need to do that. After converting to vector, we are again converted it to a matrix, and then in that matrix we are trying to, we have normalized that matrix, and then after that normalizing of that matrix, we have converted into Hermitian form. So instead of doing all this, you can title it the image matrix what you're getting, and that directly put on the Hermitian version of that. That is also fine. No need to do these steps. But one thing should be done, like whatever steps you're doing for the trained dataset, similar steps should be done for the trained dataset to for the like transformation to be coherent, so the accuracy will not get affected. Yeah, so similar thing yeah. Now, so these are the target states. So this also needs to be researched from your end. So what exactly the target matrices should be. So 50,000, 32, 32. So these are our target states. So again, the any number, this is again equal spacing the elements. So 1 is placed as equal spacing, so 0 0. 4 is placed as second, so second class 1 is kept here, and remaining all matrix like elements are 0 in that matrix. So that mapping from this vector to this vector, this matrix to this matrix transformation we are trying to do and identify that unity of separation. So yeah, okay. So this is again normalized. So here we cannot apply our unitary by SVD method, unitary by QR approaches or other approaches. Unitary by parameterization also cannot be used because this is not actual quantum computer implementation, and we cannot port this on actual computer only. Like this will need to be done on a Hamesha inspired approach only. So only approach that we can do is here is by ML. So ML, what we are trying to do is U row U dagger should be equal to our output target matrix. That's it. So that is what we're trying to do here. So similar, first thing what we're trying to do is ML model, ML pipeline is we'll try to create a class. In that class, we'll try to form forward method. What that forward method will do is it will implement this operation U row U dagger. That's it. And this is done in C-float setting. So once this is done, the same Frobenius loss is implemented here. You can implement try any other loss functions as well. So it again has the RSME or the loss value, then the unitary loss, like orthonormal loss in that, and it is added to get the return the total loss. The same reducing the RL1 plateau instead of that, since the learning rate is limited. In that case, this class function has been implemented. This is nothing but the training loop. Yeah. And the similar like transformations are done on the test data set here. Yeah. So for checking whether the implementation is correct, so what happened is after implementing the implementation of this, the output transformation and then the test transformation and the input transformations were not coherent. So the result what we're getting to verify that we have implemented a neural network. So before that also, like, we can implement a loss function kind of setting. If the loss function is near to of between the output matrix what we're getting and the target matrix what we're gotten, that for that particular class is within certain range or is nearly equal to 0, then the implementation is as correct. So that can also be done, because this is like implementation so happens like it doesn't become coherent. Like I have tried like many things. So what 2-3 times what happened is I missed the dividing by normalization part. Sometimes normalizing the input matrix, sometimes normalizing the vector was so that's why like we tried creating a function itself here, create Hermitian function, that it was not coherent. But anyways, yeah, this yeah, okay. This is the second type of the implementation. This is our method B, unitary of separation approach. What we discussed, we are first converting into vector format, then outer producting it into convert into Hermitian matrix, and same thing. So outer product is done. Baki data processing remains the same. Same thing is implemented here as well. Because the method changes, the same pre-processing is like done here. So uh, so this is again this outer product is done in np.outer section. Yeah. And the same, so the Hermitian matrices like depending on the size of our data set. So here the pre-processing if you look into, we are all converting all into Hermitian matrices, right? Converting into first like uh, take here 32 cross 32, it will be 1024. 1024, then again you have to convert that into matrix setting because you're outer producing. So that will be 1024 plus 1024 per train data. So it will be computationally exhaustive. So the size of the data set is limited to 64. Yeah, so this will be a 64 cross 64 matrix, and as per that, equal spacing of target states implementation is done. Yeah, and the similar pipelines implemented here. We already know that what the pipeline does. Yeah, and the same transformation on the test data set, and this neural network is implemented here just for verifying the accuracy, whether it is like giving the correct accuracy or not. Yeah, yeah, uh, yeah. So again, so here what your task will be to research other ways of forming density matrices, to research what exactly, how can you extract the feature vectors here as well. So those will be your task, and to get this into your like thoroughly into this concepts into your head, because this concept will be required later as well. Okay. Yeah, anybody has a question? So this is the third method, so this is the thing about the averaging method, in which the probability amplitudes are taken to be equal, as in 1 upon 5000 we are dividing it with. The same pre-processing is done here as well. This normalization is done, and so this addition we are taking and we are dividing by 5000 for normalizing it. So we are constructing a single per class, a single matrix, a training matrix, and all the test data set is classified as per that. So it's a similar ML pipeline implementation. Yeah. So yeah. So we again need only like 10 vectors or 10 matrices here as well. So the start and the end index here is not multiplied with 5000, and this is just a single target or a 10 target vector, 10 target matrices taken here. And yeah, a neural network is implemented. Instead of neural network, you can try following the Frobenius laws between the output vectors what you've gotten for that particular class and the test vectors what you're trying to do. If you're trying to find the difference between that and then place the value and then take the maximum value of that, so that will be an equivalent analog of a KNN, a k nearest neighbor, depending on the loss function. So which has the maximum or the minimum value, that will be a particular class. So you can also implement that. but we have implemented a neural network here, and you can check the accuracy. That accuracy will be 67% in that case. That results in average accuracy. So yeah, so this
Yeah,
is
I had one more question.
yeah. Please
Uh,
go ahead.
so we're supposed like for for some yeah, like for a full network, we're supposed to define the function that essentially input output function.
Yeah. So
Yeah,
I have explained you
and we're
like three
trying.
four methods for it. Yeah.
Yeah. So I was wondering how would we incorporate like a lot of convolutional nets use like max pool and stuff if you're doing image processing. Like
Yes. Yeah. So the thought process for this is like I have explained you just one of the thought processes. For that will be like where was that? Yeah. So convolution. So if you look into convolution, what does exactly convolution neural network does? First, it applies a convolutional layer, as in it multiplies the filter matrices padded
yeah,
or and we are sliding that filter matrices throughout the entire matrix. Then like a number of filters are there, 10 filters, 15 filters, 20 filters, and then after that, so these filters were also trained by a backpropagation algorithm. So after that, we'll get a new set of matrices which we pass through a ReLU function or some kind of activation function. Then we'll max pool that, as in takes a 2 cross 2 matrix and then take the maximum value of that, take it as like
yeah,
a 2 cross 2 matrix. Yeah, if you're getting the point. So this all operations will be happening after this convolutional pooling layer. Will be applying a feed forward neural network, right?
yeah,
So what we'll be doing here, basically the input vectors what you're passing and the feed forward neural network last layer what you'll be getting. If the size
yeah,
is same, what you can try to do is construct a Taylor series between those of the mapping, so that will give us a like approximate function, or you can directly like try to create a function from those given two set of vectors, or for all the set of vectors, try to construct that mapping what it is, because that last neural network layer what it will does is it will linearize the data set, because after that you are multiplying it with a linear layer. The end layer will be a sigmoid layer, before that there will be a linear layer, a weight matrices layer, right? So if that weight matrices layer will be an n cross n matrix to the dimension of the input vector, those will nothing but be a linearized like form of the vector. Because what sadly does, because after sigmoid if you try to get this now, after sigmoid you will just get the number of classes as the output. Uh, so you cannot exactly get the relation between it. So like that can be done. That is just one of the approach. You can think on your own. Like SymPy is another approach. The SVM approach, what we are given, is the third approach. So that approach clearly illustrates like what we're expecting, what 2D plot we are expecting from it. What we're expecting basically is if the number range between the vectors are 0 to 1, so what mapping, what function does the mapping from that 0 to 1 range to 0 to 1 range itself? But what is that mapping? If it is point 1, where does that point 1 maps to? What is that function? So if you look
yeah.
into, if you have,
So we're
yeah.
we're you're fine with there being like max function in the mapping, let's say. That's what I'm just trying to say. Like
No, so that's why you can look into the Serena Academy video. What does ReLU function do and what does Sigma function do? So these are nothing but the activation functions called as
no,
universal
those are
approach.
fine. Yeah, those we can model smoothly. The thing is like directly max pool and other functions. These are not like continuous functions, right?
Yeah. So we not need layer by layer. What we
Okay.
need is whole convolutional neural network. What is the function of mapping for that particular data set? That's it.
Yeah, but in convolutional nets, you try to lose spatial dependence like directly using the max pools, and so like even the final output will have like direct max terms in it.
Okay. So try to answer one question. Yeah, I'm getting the point. So convolutional neural network, what you were saying, right? The first layer is convolutional layer. What we're doing is multiplying with the filter matrices. That
Yeah,
operation is getting,
you're
but
multiplying with the kernels, and after
uh,
that,
cur-
after
linear
that they
matrices only
use
you're getting. Use ReLU functions,
max
right?
pool. No, we do max pool.
Okay. Even
Max,
if you put in nothing but loss of information, right? Loss
yeah,
of
max pool is
information.
not non-linear. Yeah,
Yeah. So that max pool, what you're doing, the ReLU, what you're doing, and the other sigma activation functions, what you're doing in that convolutional neural network setting. So input to output, all the transformation we do not need layer by layer. Add the feed forward neural network before that, before the linear layer or before the sigmoid layer, whatever operation or whatever the output vector we are getting, the transformation of that we want for every neural network. So like you can implement convolutional neural network setting in SVM as well, support vector machine as well. So if you look into our implementation, what we're doing basically is input vector, we're multiplying with the kernel matrix for every class, then we're applying Taylor series on that, and then we're getting the output, and then we're taking the maximum of all the classes
Okay.
as our target class, right? So that Taylor series after linear mapping or linear like embedding is expected. So that Taylor series gives us the function of mapping. So if you know the output vectors directly here, input vectors directly here, you can try to form a Taylor series. That is one of the approach, or you can use your like other techniques.
Okay. Thank
Yeah. If you have any doubts, you can text me more. I hope this is clear.
you. Yes.
Okay. Yeah. Okay, density matrix in super operator form. This is our next stage. Yeah. So what we are trying to do in density matrix in super operator form is nothing but super operator. By what does it mean by super operator? Here is nothing but we're trying to convert that density matrix into a vector form. So if you're trying to construct a vector form of matrix, you're just scattering. That's it. Scattering, normalizing, and those will matrix in super operator form. That operator, what you're multiplying it with, that unitary operator is nothing but the super operator. That is what the super operator method means. So since it is a Hermitian matrix, you can try incorporating only taking the first upper triangular elements of let's say n into n plus 1 by 2. So those upper triangular elements can form a set of vectors, and then those vectors can be like multiplied with a unitary or non-unitary, because the transformation here can be like open system as well. We do not consider a closed system. It can be open system. So you can implement both the unitary as well as a non-unitary transformation, and then try getting the accuracy results. What is the implementation accuracy result? So how to get the implementation accuracy result? Whatever target states you are having at the output, right? This target state. So if your gotten state is near to this target state, your gotten state is near to this target state, then so for the if the test vector let's say is in class 2, the test vector is in class 2, then the 910th element should be having the maximum probability of occurring, as in the maximum probability amplitude of occurring. It should be nearly equal to 1. If it is not nearly equal to 1, at least it should be maximum of the remaining elements. As in, if 0 has certain probability, this state has certain probability, this should be maximum. So then we can identify it as class 2. It's a direct classification like algorithm we can try to implement after this. I think in some sections I implemented. Uh, here it is not. Here we are directly like implemented a unitary, and then so if you look at this implementation, right? So this implementation exactly does that, because we are getting a output vector here itself in neural network. So this argument max, what you are doing, those are nothing but the prediction labels, and those prediction labels are summed. If they are equal to the actual labels, then they are summed. Okay, this is also not the case. I think that there are like some. Uh, I think so. Those are individual implementations. I don't remember where exactly those are implemented, but yeah. So, yeah, if you can find like those where it is implemented, I will try to put it on slide. Yeah. So after this, like there are like other novel approaches of getting Hermitian matrices, like SVD, machine learning, which we already discussed. Then here we are trying to implement this. We are first implementing unitary encoding, and then we are trying to convert the Hamiltonian version of that by minus I log u. But since the floating point error occurs, you can find after printing the Hamilton matrices, like those are not Hermitian. So this is nothing but the implementation of that itself, what we have discussed. So if we are taking SVD. So again, we are using a Penelin library. So this is nothing but our image matrix. We are taking a unitary version of that, unitary encoding of that, and then as we already discussed, this is a log of the matrix what we are trying to do. So since then we are taking SVD decomposition of that, then log of that log diagonal we are doing, and this we are getting as a Hamilton matrix. Okay, and normalizing of that Hamilton matrix or that Hermitian matrix, and if you print this, you'll not get it as a Hermitian matrix. So that's it. Yeah, and the questions, the convolutional neural net question has been incorporated. So that is again a research finding that we can implement it in our SPM setting as well. So that individual task is given to Siddhant, I think, right, Pritan?
Hello? Yeah,
Uh,
QISVM.
yeah,
Yeah, it has
yeah.
been given to Siddhant.
Yeah, yeah. So like yeah, one who asked the question can have a like we will try to assign two or more interns for a single project. So like the one who asked the question can better team up with Siddhant if you're interested in this that kind of work. So yeah, please. Um, and this is again a second technique, unitary by QR decomposition. We can try incorporating unitary by SVD as well, and the same transformations are done on test, and this is our output. Okay. Yeah. There was some error occurred here. The same code is written on a separate block. Okay. I think we have shared an updated version of this. This is a I don't know, older version, or I don't know. But anyways, yeah. And the last method is nothing but kernel matrix you already know is Hermitian. So that kernel matrix can be taken as a Hermitian matrix itself. And yeah, and we can apply a Fisher transformation on that Fisher kernel transformation U kernel dagger U dagger, and map it to certain output state or output kernel matrix that is that whose dual optimization equation can exactly give us the the support vectors like alpha values such that it separates the or classifies that equation. Okay. But this implementation was like it's not done to that much precision level, because if you look into the unitary losses and all, like those are huge. So you can try rectifying the code as well, because like as we already discussed, this is work is done like for last I don't know many like months, but for now the all the segregation of the code has been done. So the work was quite huge, and we have already taken 3 weeks, and you guys were already sitting idle after the warm up task, so we had tried to like do the work. So again, the efficiency of the code and again this minor code bugs can be rectified from your end. And yeah, you can go through other mathematical functions, like those are possible of Hermitian matrices. And yeah, that's all from like my side. If you have any questions, you can post it on Slack, or you can ask us right now.
Yeah.
Just give me a sec. Just give me a sec. Yeah, yeah, please go on. Hello, any questions to you guys?
Uh,
You can. Yeah.
no, not a question. The first tasks were I understood them well. The second LLM and all I understood. I was actually a bit confused in this, and maybe I'll just read this more again. I'm always confused by this Hermitian and something. I don't know what to tell. I'm just confused. Ooh, yeah, third one.
Hermitian matrix. Hermitian matrix are
No,
nothing
no,
but
no,
the
no.
upper. Are there?
Not in the Hermitian. Like after these set of tasks, you have said the recent tasks, right? After
So
LLM.
yeah, yeah. So
Yeah.
these two tasks you have to implement it as a common like implementations.
Mm.
Yeah, and after that, like we'll be giving you individual tasks if it is not given already. For some, we have already shared the individual task along with the code. In that code, if you look into these encodings, we have just amplitude encoded the classical data set. So in that, if you want to implement other data sets or other encodings in that to show the computational to show the advantage, as in advantage in terms of accuracy, you have to go through these basic 6 encodings. So that's the whole and sole
Okay.
purpose of giving this 6 encoding as a common task for you guys. And the feature vector extraction, linearization is a common task. So that is also. So feature vector extraction, target states ka research, and the whatever is written in that commented section, you can go through the details. And these are the
Okay.
common tasks. So I'll stop sharing my screen. Any other questions from your end?
Hello.
Yeah.
Yeah. So hello everyone. So the task that we have given to you, like the task other than what we have explained. So we will be having like one-to-one sessions for each one of you, so that we can explain you in detail again the task that we have sent you. And we will also be like forming teams for those problems in which we feel that it will require more than one person to do in order to do that. So we'll be assigning like two or three persons per task as well. So from tomorrow onwards, we will start those individual sessions, and we will be forming the teams as well. And if you have any questions, as Akshay said, you can message me or Akshay. And I think it's pretty late now, so we will close this meeting.
Yeah. I thank you, Britan, for the
Yes.
wonderful
Thank
session.
you, Akshay,
Yeah.
for your very extensive presentation. I
Yeah.
think.
Yes.
Thank you all the interns for paying attention as well. And if you have any doubts, dear.
So one last
Thank you
question:
so much.
who is using this Spinach AI? Are we using? Akshay?
No, we are not.
Okay,
I
so
think Suchi or Deep, one of
okay,
them.
so please share these notes as well. If you have like these notes, AI generated notes, so please feel free to share that into the group so that you and others may use it.
Yep, sure. Will sure share
Okay,
that.
thank you. Yeah, so Tulsi is
Yeah,
asking, yes, we can send those handwritten notes, right, Akshay?
yeah, yeah, but Bitant, like I'm hesitant to share those. We have more IPs in that and detail extension, but we can. Okay, sure. Like up to you. We'll have a discussion after this, and
Okay, okay.
we can just share the starting part,
Yes,
Yeah,
like
by
yes.
the way,
introduction.
notes was good. You can share it with us. We'll have more idea and understanding about that. No, that's why we're talking
Okay.
about that.
Yeah,
Yeah.
the same code is implemented. So fine, fine. We'll share. No issues.
Yep, yep. Thank you.
Thank you all. Bye.
Thank you. Thank you. Bye. Good night.
Thank you, actually. Thank you, Deepak.